Hi everyone, and welcome again to Monroe Live. Today we've got something that's a little bit different. Not often does a company ever give us one of their products and say we can talk about it or take it apart and use it on our show. Today I'm going to be thanking the guys over at VW who have let us have a look at the ID4 electric motor. Now this is a permanent magnet motor, and I'm going to get into a lot of the details, but in essence, like I say, that's very bold of VW. I'm very happy that they let us do it, but we are going to tell the truth on this, and that is the rule. So there's nothing I'm going to be holding back. They're not paying me, and I'm definitely not paying them. So we're going to go through this in detail, in some detail, to show you exactly what's going on with this particular strategy. So the first thing I got to tell you is that this motor's been pulled apart, and there's a short video that you're going to be able to have a look at that shows how all the different parts come apart. This product is different than most of the other guys. The strategy for Volkswagen was to look at a modular design that would allow them to use this motor wherever they wanted. So they have mounting brackets and lugs that will allow them to then take this motor and stick it into pretty much any suspension system that they want to try and adapt this motor to. So that's a different strategy than what Tesla has, where Tesla has gone and Tesla has put the motor mounts right inside the casting. Now this adds more pieces, but it gives you a lot more diversity. And with Volkswagen being as big as they are, they've got, you know, they're the biggest car company on the planet. So with them, if they want to try and retrofit something else, or they want to use that motor, let's say on a pickup truck, they don't really need or want something that's going to look like this. They want to try and stay with something that's got common mounts that they can mount the rest of the suspension to. So the strategy that they've got is great, and we're kind of interested in looking at what happens when somebody's looking at a global market instead of a dedicated market like Tesla is. So we're going to be going in and looking at each individual area of this electric motor so that we can bring you the best possible amount of information. Okay, so let's start out with the gearbox. Normally this is about the first thing that we're going to pull off, and as you can see right along here, you can see that there's this black stuff. That's RTV. RTV is used as a sealant here. I'm kind of a big fan of RTV, and the reason for that is because you never get a leak path. This is a good idea from the standpoint of closing this thing together, but let's talk about the overall strategy. So the big challenge, or the big issue that they had with the gearbox was they had to make sure that they could make the lightest, most cost-effective gearbox, but they also wanted to make sure that it lasts the life of the vehicle service. Now, I don't know what the VW's lifetime is. Tesla is shooting for 1 million miles, but I'm not sure whether the rest of the car is going to be able to survive 1 million miles. So at the end of the day, we're looking at this product right here, and we're seeing things that are different than everybody else. Alrighty, so let's just pull this apart a little bit and have a look at what's going on inside. So we're going to look at this shaft right here first. This shaft fits into, we're going to move over here. This shaft fits into this part of the electric motor. So you've got a dead accurate alignment between the spline that you see in here, the female spline, and this male spline that you see on the other side. Now, what does that do? Well, that allows Volkswagen to go with 3 bearings instead of 4, like on most of the regular products. So you can see in here that there's 1 bearing down below. Normally there'd be another bearing somewhere here, and then you'd have these 2 bearings. They're kind of common. Now, the next thing you notice is those bearings are quite small compared to what you get with Tesla. The Tesla bearings are gigantic. Now, this is one of these things where people make decisions. This product is supposed to be for the life of the vehicle. What is their life versus what Tesla's life is? Now, Tesla had said in the past that they want to have 1 million miles. That's quite a lot. So I'm not sure whether they're counting on the ball bearings to do that or whatever, but this is a clever design because they can get rid of one of the bearings that normally would be in this type of an engine. I don't think I've ever seen one up till now that has just the 3 bearings. So what does all this stuff do for them? Well, what it does is it reduces the amount of friction. Anytime that you can reduce friction, you're going to increase mileage. And so from that standpoint, this looks like a pretty good idea. One of the big problems with reductions of bearings usually has something to do with noise. And so to overcome these issues, Volkswagen did quite a bit of a testing, especially when it comes to noise and acoustics. They wanted to make sure that this was going to be as quiet as it could possibly be, and that's why there's the very tight tolerances between this shaft right here and the female shaft that's on the, or the female receptacle that's on the rotor. So everything here looks pretty good. We were pretty happy, and Volkswagen was very proud of what they did. However, when we were looking at the product, we found burrs. So let's look under here, and you can see that this is what we would call a plunge cut. And it's fine, except on the casting, we found these burrs. Volkswagen was not happy to hear about that, and they're looking into it. Now, this is a pretty good design as far as I'm concerned. It's a cost-effective design for sure. I like things like the RTV, and I like the fact that they could figure out how to get rid of another bearing. This was, to go to 3 bearings on a jet engine was a big deal. And when it was done a long time ago, everybody else copied it. I'm sure that everybody's going to be copying this. Okay, let's move on to the cooling strategy. Now, the cooling strategy on here is a little different than everybody else, but before I do that, let's talk about what materials were used. So over here, with these two components here, these are high-pressure die castings, and they pop up at 383 or 384 aluminum. Sometimes our machine said it was 383, sometimes it said it was 384. The center section is a low-pressure die casting, and it's a 3105. That particular component was looked at by Volkswagen, and what they thought was maybe we could go to an extrusion. That extrusion turned out to be too much of an effort or an issue, mainly because probably they had a lot of machining that they would have had to do, and sometimes an extrusion will come out heavier. But at the end of the day, this is the way they went. It seems to work really well for them, and so I'm thinking that this is going to be pretty good for them. The strategy that they came up with, where and we're going to show you this in a second, but in essence, the coolant is going into the inverter. This is the inverter, and then from the inverter, it's going into the motor. So the inverter has turned out to be the #1 issue that they want to try and cool first, which is the right way to do business. And then when you take the inverter, and I'm not going to do this entirely, but if you take the inverter and you pop it in place, like so, then what happens is these different outlets will connect together, and it mates all your different cooling attributes together. So that's kind of like the overall strategy. Let me move this out of the way so I can get to a little more of the detail. So let's look at what we've got when we start seeing inside here. So if we look inside, again, we're looking at the RTV that I showed you a second ago. We're looking at how they've sealed this thing off, but the circulation, I think, is a lot more important than everything else. So the coolant is going in through this port right here, coming out in this slot, and then heading into the low pressure die casting, which is also the stator housing. And we really liked is that as the coolant is flowing, it's going through this passage, connecting into this one, going into that one, turning around. So it's cooling the whole outside, basically with a racetrack or serpentine kind of actuation. And then ultimately what happens is the hot coolant is now coming out here and heading back. So again, the brilliant part of this is they've eliminated an oil pump, an oil filter, a heat exchanger, and that's something that Tesla has on board that these guys don't have. They don't have to do it because if we look over here, you can see this is the oil filter, this is the pump, and this is the heat exchanger that Tesla is using that the VW doesn't have. So this is a good idea because you're eliminating a system. So in this particular case, Volkswagen has basically jumped ahead of Tesla in getting rid of these three components. So their objective when they were creating this, this motor and gearbox assembly was to try and figure out how to do a simplified version of the product and keep that cost down. They also thought it'd be great if we could figure out how to do the inverter first, because really and truly, everything's about electronics. The motor doesn't really care how hot or cold it's going to be. It's all about this thing right here. Now, the one thing that we did see that totally blew us away was these little tiny squirt holes. So let me get over on this side. So if we look right here, so this little teeny tiny hole is, I think, the bleed. So the coolant is going in through this port right here. It goes all the way around the whole of the housing, and then this is the out port, which will go to the return line for the heating system, for the cooling system. So that little bump right there, that little hole, I believe is a bleed, just to make sure that there's no air inside the system. Okay, so let's move on now, and I want to talk a little bit about the rotor and the stator. The stator is this part right here, and the first thing you're going to notice is that this does not look like that, okay? This is from a Tesla, and this is using wire wrapping, okay? This is a hairpin design, and quite frankly, I like the hairpin design better because in essence, I can get about a 60% fill versus a 46% fill over here with the typical windings that you'd see in an electric motor. Those kinds of things kind of tell me something else. It means basically that I'm probably going to use a different kind of a magnet. And that magnet is probably going to have less of something called dysprosium in order to make it work. And dysprosium and neodymium are the two most expensive parts of any magnet. So if we have a look at that, let's look at right now the way the motor is put together. And in essence, what they're using are 4 big long bolts. This is the bolt right here, and in essence, you push it through, and then you run it down with a nut. So our guys like this because it allows you to compress the laminates. We'll talk more about laminates in a minute, but it allows you to compress the laminates and the magnets, and it allows you to do that at the end and then keep them tight, because the laminates, the magnets, and the spinning all cause a force that wants to basically blow the electric motor to pieces. By doing something like this with this long motor, or sorry, this long bolt, you're holding it together and you're doing it in a cost-effective way. The problem is, I don't like bolts. I'm going to talk more about that in a little while. One of our things is that I talk to our customers all the time about getting rid of threaded fasteners. They're the highest and most problematic of all of the different components you can put in any product. So a second ago we were talking, and the electrical guys were telling me, well, they liked it, and I already told you all the reasons why they liked it. And I said, all right, I don't like the threaded fastener, so how can I get around this problem? Well, the way to do that is by using something that would look like that rod, shoving it through, and when it comes out the other end, you clamp everything up in a fixture, and then you do something called radial riveting. Radial riveting works faster than a threaded fastener, and it'll never come out, never. It's always going to be there. Whereas threaded fasteners, if you looked at some of the other ones I've talked about, as soon as they're side loading on these, they start to undo. And the reason I know that is because when I was at Ford, I was in charge of the sealing and fastening lab we had at Engine Division, and we found that any side loading on a threaded fastener, especially with a nut, is a real problem. So I like the idea of holding it together without any adhesive. I don't much care for the idea of using a threaded fastener, and there's a way around it. So that's free consulting for VW. So let's talk about one other little aspect that we thought was interesting. The shaft, the rotor shaft is not heat treated. Now this was a conscientious decision on VW's part, because they said that if they put threads on here, they would be easier to deform, and they didn't like that idea. So instead of having a bearing lock nut, which is kind of like what everybody else does, they put in the 4 bolts, and that saved them from getting that shaft heat treated. And I think that that could work. That's a lot of experimentation to make something like that happen. So these bolts right here, when they're run down, they're going to be going through the same process that I talked about before. You run them down to torque, and then you're going to squeeze it a little bit more, which will put a load in this shaft. That's going to allow them to be into a plastic state, and that'll hold it together even better. So kudos for how they did it. I would just do it differently. Do something here. Let's just pull off the cover plate and talk a little bit about the magnets. Right here I have the magnetic array for the Nissan Leaf. Over here I've got the Tesla Model 3 and Model Y. And over here we've got the Delta arrangement that Volkswagen has decided to go with. So you can see this looks a little like that, but it's not the same. And quite frankly, the one other thing that I thought was kind of interesting was, let's have a look at the green cloth here, and this will tell us what it looks like the magnetic array looks like in this vehicle. Now, have a look at this. See that pattern right there? Okay, that pattern is done like that to get rid of noise. Okay, noise abatement is a big thing with electric motors. If we look at the Nissan product, you can have a look here, and you can see that there's only one offset. If we look at the Tesla, you can see that they've got a small one at the beginning and the end, and a long one in the center. These two will equal that one in the center. And that, again, is done for noise and performance. I have never seen this before, but you know what? I like it, because this gradual offset, anybody who's ever gone over a train track in the United States knows that when you hit that train track, or when you hear the train going over where two train rails come together, you'll hear the-thunk, the-thunk, the-thunk. If you go to any of the high-speed trains, like the ones in China or Japan or in Europe, they don't make any noise. And the reason for that is because they're cut on a bias. So America, we cut them this way, so they butt together. But in Europe and in Japan and China, they cut them on a bias. And that bias allows the wheel to go over it more smoothly. And that's kind of the same thing that's happening here with the green cloth, telling us this probably will give it a little more performance, but on top of that, it's also going to help it out with noise. And noise is a problem with electric motors. So let's look down here at the laminates. Now, I've talked about these before. We pulled out a couple of laminates. We pulled out a couple of these things. And you can see here that this is where a magnet goes, that's where a magnet goes, and this is where a magnet goes. So what's all this other stuff? Well, this is called skeletonizing. And all they're trying to do is get rid of whatever weight they possibly can. This is a very good idea. There's no reason in the world why we need that extra weight in order to make the laminates work and do their job. So by getting rid of it, we've seen this on pretty much every motor, but this is one that's kind of done a very good job on skeletonizing. So how do we hold this whole system together? Well, right here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 threaded fasteners that basically go through this hole, through the stator housing, and into the front end of the gearbox. Okay, so now we're going to wrap this up by talking about the inverter. But before I do that, there's one thing I want to kind of bring the audience up on. Monroe & Associates, we've worked on everything from Barbie to the space station as far as designing new product. One of the things that we've found that changed the minds of people that we work with is what we call the Good Design Principles card. It's this thing right here. In it, on one side, we've got some good design principles. On the other side, we've got some rules and regulations. But in essence, what we're looking at is we want to design the product so Bob can put it together. And Bob is the blindfolded, one-armed builder. Now, why would I want to do that? Well, because a robot is basically a blind, one-armed idiot. Okay? It only does one thing. It picks something up, it puts something down. Remember that ad where the big, yeah, kind of like that. So a blind, one-armed builder, if he can put it together, a robot can put it together. And if a robot can put it together, then a man can usually do it faster, cheaper, and better, except for something called the 3 Ds, dirty, dangerous, and drudgery. So that's one aspect. The second thing is this right here, okay? The part value challenge. There's basically just 2 rules. Does the part have to move? I don't care if it does right now. But in a new design, could you get rid of that movement? Does a part have to move? Or does a part fundamentally have to be a different material? Okay? When you ask those 2 questions, you wind up with penalty points if you can't say yes. And in essence, for us, the part value challenge is telling us that that part should be either eliminated or combined with other parts. Another way that we've got to make things happen in a new way is right here. These are the poor quality drivers. If you look at almost anything that's modern, you'll see that it probably snaps together. In the olden days, they used screws. And why did we move to snaps? Because they're better? People say, oh no, snap fit's not so good. That's wrong. And I can make anything snap together, including wood parts. So we can design now what we could never design in the past. If we can just figure out how to get rid of fasteners, and that threaded fasteners is what everybody usually says, but really and truly, it could be threaded fasteners, it could be rivets. Anything that's a slave fastener is a problem. So these are things that we would normally do. Now, I've said that I don't like some of the threaded fasteners that I see on this product. I think there's too many of them. But let's look at everything that you've seen so far. This product has simple vertical or straight down or top down assembly strategy. This is great for Bob. The Bob philosophy of being able to put it together with one hand behind your back and your eyes closed, that's a great idea. That's the kind of idea that we really want to have. So I want to look at a product with that philosophy. And when I look at this, there's a lot of good things here. So we're going to talk about the inverter so let me just show you the one thing that I kind of like. It's hard to really show exactly what's going on, so I've removed the case over on this side so that you can see, so I can expose the leads here to the electric motor. And if we look at the way the inverter goes, I've shown you this once already, but in essence, this is going to go right over the top of these two components down here. So you're going to be able to drop the inverter on top. It goes through the casing, and then I can fasten those screws. So that's good top-down assembly. But there's more. So we look inside here, and we might as well start right on the top. You'll notice that there's a lot of threaded fasteners for this. Like I said, in Germany they must be able to get threaded fasteners 10 a penny. So let's take off the lid, and when we flip it over, you can see that there's something here, this black thing. This is an EMI seal. This basically is keeping any sort of electronic discharge in or out of this box. You don't want to have that sort of thing. And so we move that over there. Now, I like the idea that this is all vertically down. I like a lot of what I see. I mean, everything here is vertical. I like that. That's good. The problem is, look at all the screws holding it in place. I don't understand it. This has got more threaded fasteners than anybody. Nobody has as many threaded fasteners as what we've got here. So next thing that comes off is the top cooling plate. And this is basically a heat sink that wicks away heat from all of the components down below here. Now we've got the next layer of componentry, and under here you've got the cooling tray. These are the pins. So the coolant that we talked about that goes through the electric motor comes in here, flows around here. That goes around these pins. These pins then wick away the heat, and that means that these IGBTs here aren't going to get terribly hot. So we got this down. Now, one of the things that we really liked is this doodad right here. Let me just put this down. This is called a bleed resistor, and the bleed resistor fits right here. It's glued down. So when I take this board and put it over the top of the bleed resistor, I only have to make these two connections down below. Now, that's what we have here on the VW. This is what we've got. This is what we've got over on the Nissan Leaf. This is a monster size, and the Leaf is a much smaller capacity electric motor. Now, this is kind of interesting. This is my least favorite. This probably comes in second. Oops, sorry. Here's the Tesla. This probably comes in second for me. This bleed resistor right here, which is screwed down. This could easily be a snap fit. I can make snaps either on the plastic or into the aluminum and snap that in place. With the glue, it'll never come off, never. And by the way, nobody's going to service these things. But my favorite still is the bleed resistors that you find on a Tesla. And then they have their own little thermal pad that goes over the top of them. I like the idea of putting this kind of stuff on the boards because I know that it's going to be right all the time. This requires manual assembly or robotic assembly, depending on how fast you're making things. Let's take out the cooling tray. Again, I like this design because it's vertical down, but it's also cleverly done. So let's take out the capacitor. Sometimes I can get this, sometimes I can't. Here, let me do it this way. So this is your capacitor, and that's basically what makes the electric motor work. Then you've got a secondary capacitor that comes out and then you've got your bus bar. That comes out. Now, have a look at, and then over here we have the connection that we need to get to the electric motor. Over here is the connector that comes through, and then basically it's bolted in place from the backside. When I first saw this, I said, "How come there's no seal?" But the seal is on the male connector. The female is basically sealed off around this outside edge and around the inside edge. So this is a good idea. There's lots of good ideas here that make me think that VW did a great job. My only complaint is, holy mackerel, I cannot believe how many threaded fasteners. I have never seen this many threaded fasteners on a product this size or this type. I think that one thing we should note is that Dr. Deming used to say that with threaded fasteners, if you put more of them in, your quality is going to drop. And the reason for that is because threaded fasteners that's the wrong name. These are called threaded unfasteners. They're threaded unfasteners because at the end of World War II, everybody complained about componentry that was on different products from different parts of the world, especially Britain and Canada and Australia, where they were using things like Acme and Whitworth. They had a hard time getting the bolts off. They were too tight. They didn't like that. Products would break and they had a hard time getting the bolts off. Well, with a 60-degree inclined angle, the angle of the thread is at 60 degrees, and Acme is at 15, which is a locking angle, and Whitworth, it's just as bad, 8 degrees or whatever. In square threads, these things are made to stay together forever. We don't use them. We use a 60-degree threaded unfastener, and that's what it does. If it vibrates, if it thermal cycles, if it gets any side loading, it undoes itself. Now, how do I know that? Because I used to be the co-captain for sealing and fastening at Ford Engine Division. And I can tell you for sure that we ran a gazillion experiments, and threaded fasteners are not your friend. Get rid of them. I highly recommend that if they're going to do something like this, there's only one way to hold these things in, because these screws are too small to go into yield. So I would highly recommend that you glue them, Loctite, something like that. But if it was up to me, I would figure out how to sandwich these things, snap them in place, and done. That's it. You aren't going to be tearing your car apart to change or fix an inverter. I just don't think it's going to happen. I think that this is just like your ignition module. Nobody fixes those either. So with all of this, what did we find? Well, on the upside, there's a lot of good things here. A lot of interesting product. They've done a great job on eliminating an oil filter, a pump, and a cooler. I like the fact that they've gotten to use the coolant as opposed to oil. I kept saying oil. There's probably going to be a lot of deletes that you're going to wonder what's going on, but that's one of the things that's happening there. On the downside, I really wish that I would have saw less fasteners. I think, quite frankly, that Volkswagen did a pretty good job. So, and just for those folks who want to know, we already tested this is a low pressure die casting, and it uses the same material as the housing. So, at the end of the day, this is a very good example of the way a product should be designed, I think. A couple of exceptions, but for the most part, I like what I see. Thank you, Volkswagen, again, for allowing us to film your powertrain. And I'm not sure if they want this back, but you can have it back, but I don't think it's going to work anymore. So anyway, until next time, thank you again.